Good morning. My name is Azad Mashari. I'm a cardiac anesthesiologist here at TGH. Just want to thank the organizers, Dr. Kuzimanu, Dr. Razak, and Ms. Sabasan for this kind invitation. When I first came on staff at TGH, I showed up at the right time, and one of my colleagues, Max Mineri, who's now in Leipzig, had just managed to secure the funding and organize this perioperative imaging lab. We were both perioperative echocardiographers. That's how we became interested in perioperative imaging, and especially 3D echo. So the lab started out as a facility to investigate applications of 3D echo, and now we more generally look at applications of all perioperative imaging, both educationally and clinically. Over the past few years, we've been making more and more models for clinical planning, mostly for minimally invasive procedures and complex congenital cases, but increasingly also we've been getting referrals from surgeons, especially Dr. Kuzimanu, who's been very supportive of our work. I joke as an anesthesiologist, the only thing we can do independently is Botox injection, so it's very helpful to have the support of our interventionists and surgeons in getting this work done. So no financial conflicts of interest or otherwise. This work is supported by the Peter Mark Cardiac Center Foundation, which has been very generous in their support of our lab. So I've been tasked with giving an overview of the technology involved in creating 3D models and their applications, especially in the context of cardiac tumors. So I'll start out by talking about some basic concepts, describe the basic presentation and visualization tools that are used for 3D models, go over the basic process that's involved in the creation of the models and its limitations, talk about issues surrounding guidelines and appropriate use of such models, and then talk about some of the limitations that currently exist and future directions. So basically, what are they? How can you see them? How are they made? What can they do? What can't they do? And what does the near future hold? So what we're talking about here are patient-specific 3D models. So these are models that are based on the patient's own medical imaging. So any kind of three-dimensional modality could theoretically be used. Specifically, CT, MRI, and 3D ultrasound are the most commonly used. But data from other modalities such as PET can be incorporated. Models can be dynamic or static. So 3D echo is really four-dimensional because the images are moving, and you could theoretically make digital dynamic models. But those are actually relatively less used at the moment, but they're definitely coming into use more frequently. Most models these days are static models. And basically, the central, sort of the key player in this talk is a digital 3D model, which is basically represented something like this. And what that code represents is a 3D mesh. So it's defining the surface of the forms by providing vertices and edges that connect them into this triangular mesh that creates the form. So it doesn't have much information about the volume inside the surface. This will change over time as other more complex file formats become available. And in addition to just having the geometry, you can have colors or textures assigned to those areas as well, and those can correspond either to just arbitrary colorings to improve visualization, such as we used in this model, or they can actually correspond to data from another imaging modality, such as the growth rate in certain areas or PET signals. How can you see them? So the traditional visualization modality was 3D on-screen rendering, and with the technology now, this is quite powerful and can create a pretty good impression of depth, but it has certain limitations. Stereoscopic and holographic displays are coming into increased use. 3D printing is definitely getting a lot of attention, and virtual and augmented reality are also modalities that we work with quite frequently. In terms of how they're made, so the first step is obviously imaging. And up to now, as modeling has been fairly new, we've been using retrospective imaging that the patients have had for other indications. So the imaging has not been optimized for modeling. As modeling is becoming better known, we're now seeing cases where the surgeons are actually ordering imaging specifically for modeling, and we have a chance to actually optimize the settings and acquisition of the image to facilitate modeling the entire structure. I'll talk about the different imaging modalities and the pros and cons of different modalities. But basically there are four steps involved. So the first is the imaging. The second one is resampling to what's called isotropic resolution. So that's a resolution that's the same in all three geometric axes. I'll give a bit more detail about that later. This is done to facilitate the segmentation. That's the next stage, where you highlight the key structures in 3 dimensions. The gold standard for this is still for it to be done manually, slice by slice. which is extremely time-consuming and unrealistic in most cases. So most segmentation these days is done semi-automatically, and there's a lot of work being done to fully automate the process, at least for most cases with fairly common anatomy. The final step is to actually take what's called the voxel model, which is essentially a model that's made of these voxel Lego blocks, into a mesh surface model that can then be used in all the remaining workflow. In terms of the pros and cons of the different sourced imaging modalities, CT is by far the most commonly used imaging modality for us these days, in part because it's the most common imaging modality that's used in 3 dimensions. It has near isotropic resolution, so you can get it down to 0.5 millimeters in X, Y, and Z axes. Ideally, it should be cardiac gated to minimize motion artifacts, but there's some exceptions, such as this case where we weren't able to use a cardiac gated CT. It's very good for segmenting things like bone or contrast-enhanced structures, but it's not as good as MRI or other modalities for soft tissue distinctions. Now, that may change as dual energy CT becomes more commonly used, as dual energy CT is able to create better soft tissue contrast, but it's still not available in most centers. MRI gives the best tissue contrast, but unfortunately in adults, because of the time and technological requirements of the acquisition, you get really good resolution in the 2 axes that you're looking at, so this image looks pretty sharp, but the space between the slices is typically 5 to 8 millimeters. So it's very difficult to actually make a good 3-dimensional model out of MRI in adults. In pediatric cases, because the patients are smaller and because MRI is all you have, we're able to get thinner slices, and so most pediatric cardiac modeling is done from MRI. And the group at Sick Kids in radiology is quite active at doing this, and they've been pioneers in the field. And finally, where our work actually began was with making 3D models out of 3D echo. And 3D echo gives you the best temporal resolution. So for fast-moving objects, especially cardiac valves and valve-related pathology, it's ideal. But of course, echo has limited spatial scope, and even as technology has improved and we now have much better echo probes, and the computation behind the echo machines has improved significantly, we're still pretty limited in the physical scope. So we can't model a whole heart, or we wouldn't be able to model a very large tumor. But certainly masses that are largely intracardiac can be captured this way. It's the most technically challenging data set to model, largely because of its complex geometry with its frustum-shaped voxels that I'll talk about shortly. Also, because 3D echo is relatively new, the DICOM encoding is not standardized. So CT and MRI can be opened in any image reading tool, any DICOM compatible reading tool, but 3D echo requires specialized and usually vendor-specific software, which definitely complicates the procedure and makes it less accessible to many centers. Just talking briefly about voxel geometry and its importance. So isotropic means it's the same in all 3 directions, so basically a cube. So CT is essentially isotropic or very close to isotropic, typically about 0.5 millimeters each way, so a bit like a Rubik's Cube. MRI has pretty good resolution in the 2 axes that you're looking at, so this would be the kind of image you would normally see on your screen, but between the slices that are much thicker. So you have these sort of rectangular prisms as voxels. And for echo, the voxel shape is much more complicated. And not only does the dimensions vary in the 3 axes, as you move away from the probe, they become larger. So the resolution not only varies by orientation, but it varies with distance from the probe. So things that are further from the probe are captured at lower resolution. This is illustrating the basic segmentation process, and this is actually this model here from the first case that you heard about. So we have the CT scan here in 3 planes, and the voxel model that's generated from it in the lower left corner. And you can see some of the artifacts of the segmentation there. If you look closely, you can see there's kind of the striations along here that represent kind of the slice-by-slice work. Here we segmented the blood volumes, not the myocardium, in part because the myocardial boundaries we couldn't see very clearly, and we knew from MRI that the myocardium was not invaded except for one region that was in question near the LAD. But we couldn't see that clearly in this data set. This data set was not gated. We had a gated CT for this patient, but it only captured just a sphere around the heart and did not capture the great vessels, which were actually quite critical in decision making about whether the tumor could be taken out and how it should be taken out. Part of the problem with cardiac gated CTs is that they take up a lot more radiation. because you're basically obtaining an image at 10 points along the cardiac cycle. So it's almost, not quite, but almost 10 times the radiation dose of a regular CT for the same volume of acquisition. This segmentation was done semi-automatically, and you can actually, if you look closely, you can see that in part of the, can the cursor show up? So up here you can see the texture is a bit different, and here you see the striations. So these striated parts were done more manually because the automated algorithm couldn't pick them up very well. But the section that actually has a more realistic contour, these were done automatically by a contrast detecting algorithm that followed the contrast levels and stopped when it hit a sudden change in the Hounsfield units. So once we have the voxel model, we import that into a mesh editing program. In some software, this can be done all in one piece of software. But here, you do a bit of smoothing to remove some of the artifacts. You remove any things that were accidentally highlighted by the automated algorithms. And it's important, again, at every stage to go back to the original image and to check the key structures to make sure that you're not introducing errors and you're not creating things that weren't there in the first place. And I should add, a lot of this work can now be done on very high quality free and open source software. That's a group at Brigham and Women's coordinates a 3D Slicer project. That's a very large medical image computation project that was originally done for neuroimaging, but now supports cardiac image and segmentation as well. This particular screenshot is from Autodesk's Mesh Mixer, which is freeware. And I'll just show you the final rendering of the product here. So one of the benefits of rendering is that you can easily rotate and manipulate the object. You can actually zoom in and out quite a bit. You can even technically walk into the object and look at the inner structures. And you also have the option of sort of showing and hiding different structures. And in this case, we made the tumor transparent just to highlight some of the vascular involvement. So for example, the pulmonary vein that's penetrating and encapsulated by the tumor. As I mentioned, we segmented the blood pools and not the myocardium in this case because that was the thing we could see most clearly. So looking at applications now. So again, this is the digital model as represented in the computer, but this can be 3D rendered, it can be 3D printed, and it can be viewed through a virtual reality or mixed reality visualization device, as well as stereoscopic or holographic displays. Each of these have their own sort of strengths and weaknesses. The rendering we just had a look at, so 3D printing has been getting a lot of attention, especially from the radiologists. And the Radiological Society of North America, which has, I think, one of the biggest medical conferences in the world, is the major showcase where 3D printing technology, segmentation tools, and devices are on display. And it's an amazing conference just in terms of its scale alone, never mind the actual content. So, 3D printing is, of course, the most accessible form in terms of understanding, so it's very good for patient communication. It doesn't require any learning curve of special manipulation techniques to view and understand what you're looking at. With life-size models, you get a very good representation of the pathology and the structures involved and the geometry. And it's probably most conducive to kind of reflective viewing than any of the digital modalities, and much less straining on the eyes than all the alternatives. Unfortunately, in terms of resources and costs, it's the least accessible, and it's, of course, the least portable as well. You can't email it and send it around electronically. There's a growing range of materials that we can use now for printing, so to capture different colors, different textures. There are printers that can print with multiple materials simultaneously to get a range of mechanical properties. You can print with biocompatible materials. You can print with tissue, on-tissue scaffold, so you can have cell lines that you then place on a 3D scaffold. And the field is growing quite rapidly and the cost is dropping, and most large centers are acquiring 3D printing facilities in one form or another. The main limitation is the scaling. So you can't interact with the model as well. You can't look inside of it as easily. You can't non-destructively open it up. And we're still not able to capture the mechanical properties of the tissue very well. And that limits our ability to use them in simulations to some extent. Virtual reality is another big application. And this is a slightly motion sickness provoking video from our lab. So this is our congenital heart disease atlas. So there's our lab manager, Joshua Hyanson, who's the technical brains behind most of this work. So he's wearing the goggles, and you're seeing on the screen what he's looking at. There are 2 cameras in the room that are looking at him and checking the position of his hands where he's holding these controllers. So he's using those controllers in the environment to manipulate these heart models. And right now he's sort of going inside it and checking the scaling. So
welcome everyone. Today we're going to talk about transesophageal echo for aortic valve stenosis.
YouTube autoplay function. So as you see in virtual reality, you're in a completely artificial environment. You don't see any of the outside. And that's the difference between virtual reality and augmented or mixed reality, where you're actually seeing the real world with 3D images that are projected on top of it. So this is just a demonstration of one of our teaching phantoms for doing echo. So this is a heart model that was made of a real patient CT, and we also then use the chest anatomy to model the bones. And this model is echogenic, so the actual physical model is down here. That's the gel model. But for novice users, they can actually look at it with a screen and have the 3D model projected on top of it so they can see what's inside the model. And that helps novice users to learn probe positioning and learn the landmarks. But a similar technique is being investigated for surgical guidance. So for example, for localizing tumors in solid organs. And our general surgeons here have used it a couple of times to try to home in on liver tumors. Beyond visualization, one of the more exciting applications is procedural stimulation. And this can be done physically. So the Sick Kids group, the radiology group, started printing these ACHD hearts from MRI. And they were initially being used in radiology teaching, and now they're collaborating with the general surgery program, with the cardiac surgery program. And these workshops are now integral to the residency in cardiac surgery. With these models, these are printed in soft plastic, and they allow the staff surgeon to demonstrate the procedure, and there's a recording of it that the trainees can watch, and then they can perform the procedure themselves on these models. So unlike what was happening previously, before they ever perform any part of this on a real human being, they've already performed it a few times on a plastic model. The fidelity is not perfect, the tissue consistency is not exactly the same, but it provides great understanding of the complex anatomy that's involved. And in fact, because the tissue, I was speaking to one of the residents recently, and he mentioned because the tissue is actually more delicate than real tissue, if you can manage to get your sutures to stay in this, you have a much better chance of success in real tissue. The same thing can be used by more experienced surgeons to actually plan or rehearse complex procedures that they may be feeling a bit uncomfortable about. Beyond physical simulation, we have virtual or mixed simulation. So these are situations where you use virtual reality or an artificial environment to simulate a procedure. The big limitation is haptic feedback, but the main advantage is your ability to manipulate the model and to control it. So these would, for example, allow us to have a simulation where you model different ways of slicing a tumor or different ways of performing the procedure. That requires capturing some of the mechanical properties of the tissue, which is our major limitation at the moment. But that is something that's improving with time, especially with dynamic imaging. Because if you have an imaging modality where the tissue is moving, you can use the velocities to estimate mechanical properties of the underlying tissue. There's a very large growing field of computational simulation, which may or may not include visualization. It's used most heavily now in interventional cardiology to do things like prosthetic sizing and estimating complications. So in this study, for example, they were looking at transcatheter mitral valve implants and predicting LVOT obstruction, which is a common complication. And they were able to actually do it quite accurately with a fairly simple static model of the heart. You can also do complex measurements on these, and I know there's work being done about this because you sort of see mentions of it in abstracts and papers. I think a lot of it right now hasn't been published because of various sort of IP issues. there is work being done in radiation oncology. Again, most of that's I haven't seen published, looking at computation of volumes, looking at serial imaging and computation of response rates and changes in growth rate. In terms of cardiac tumors, like most of the 3D printing field, the evidence base currently is limited to case reports, and these are pretty much all the case reports that are out there for cardiac tumors. There's a delay in these getting published. There's many more centers that are doing this now than what's been shown here. In most cases, they're taking a CT, or in pediatric cases, MRI, and following more or less the same procedures that we did in modeling these tumors. There are a couple of case series, but nothing where they've actually been able to look at patient outcomes. So we don't really know from an evidence standpoint whether it makes a difference, although it's difficult to argue in some cases, especially the more sort of rare and complex cases, that it wasn't helpful. Certainly, the only outcome measure we have is feedback from surgeons, which is overwhelmingly positive. The best study in any sort of cardiac 3D printing is this one. It's a multi-center study where they looked at 40 congenital cases, and they had the surgeons assess the patients using their standard assessment and standard imaging and come up with a surgical plan. They then made a 3D model of the case, gave that to the surgeon, and again asked for a revision of the plan. So at that stage, they found that about 19 out of 40 cases that they had across 10 centers, that was almost half the cases, the surgeons changed their plan. Then and most interestingly, 4 cases that were actually going to have univentricular palliation ended up having biventricular repair successfully, which is a major difference in prognosis for the patients. And then they followed that to what was actually done intraoperatively, and I think with the exception of one case, the 3D printed plan was the one that was followed. So that was a major change in decision making in that context. It's very difficult to do these studies, and I thought they used a pretty clever design to get around a lot of methodological issues. And we've considered doing something like this for complex valve repairs for the aortic root and mitral valve, but it's still on the drawing board. In terms of institutional support, the RSNA is really the forefront of trying to institutionalize this and bring this to widespread adoption. They're the first group that's published any kind of appropriateness guidelines. I'll talk about these in a second. They've also lobbied the AMA quite heavily to get, right now, Category 1 CPT codes for 3D printing, which are not codes that can be billed, but they're codes that they use for monitoring usage, and that eventually will, if they're either dropped or they're adopted into Category 1 codes, which will allow billing and compensation. The actually interesting factor about that is the major income source of the AMA is the copyright on the billing codes, which I was surprised to find out. So the AMA is primarily an IP organization. So this document was published in 2018. There's an update of it coming, focusing on cardiac specifically in 2019. But of course, because the evidence base is quite limited, this is the section on cardiac neoplasms from the draft that'll be published soon, and the answer is 7. So how appropriate is 3D printing for cardiac neoplasms? We get a 7 out of 9, so that means usually appropriate. This is based on the case reports, all of which were on that previous slide. That seems reassuring until you notice that cardiac transplant also gets 7, based on one publication, which is interesting because the thing you'd be modeling is presumably the heart that's coming out of the patient. The anastomosis may be useful, and this one publication actually turns out to be a case where a heart transplant was done for dextrocardia, so they required some advanced planning to figure out how to position the heart. So the guidelines are there, and it's good that sort of this flag has been staked, but there's still not very much substance to them, and of course that requires more evidence over time to build up. And in terms of limitations, of course the models are only as good as the source imaging, and of course they can easily be much worse than the imaging. One of the big problems is this illusion of certainty that you get from the 3D model, whether it's printed or rendered. Because during the modeling process, if you see a kind of a blurry gray voxel, you either include it or you don't. You can't kind of easily mark it as an area of uncertainty clearly. And there are some ways sort of around it. If you're looking at specifically focused areas, you can use color coding or other things, but there's no systematic way of doing it easily. It's a multi-step process, so there's multiple sources of technical error that can be introduced. And again, as I said, at every step it's very important to verify the model against the source imaging. All of our tools allow us to superimpose the model at every stage on the image itself and to review it with radiologists, and especially any critical areas get reviewed. Mechanical properties are still poorly captured, as I mentioned. And of course, in terms of widespread adoption, the access is still quite limited, largely on an experimental basis at centers that have big foundations that can support this kind of research. It's even quite difficult to actually get research funding for this because it's fairly novel. The evidence base is still limited, and we still lack good guidelines and appropriate use criteria. And our infrastructure, whether in terms of cost recovery or the organizational models, and even support in our PACS and EMR systems, is still a work in progress. But there are a few interesting developments coming in the near future. One of them is multimodal image fusion, which is kind of becoming more and more mainstream. Technically, this has been possible for a long time. The main blockage is the fact that each vendor kind of prevents you from using their tools with some other vendor, and most centers have different imaging tools from different vendors. So it's been quite difficult to bring these things together. There's a growing move towards standardizing these protocols, but even at this stage, you still need to have sort of a equipment from one suite to be able to do this. This example in the image is from combining fluoroscopy and echo. So they use the position of the echo probe as seen on the fluoroscopy to position the echo image on top of the fluoroscopy, and it's quite useful for interventional procedures. And transcatheter puncture, in this case, is what they were evaluating. What this will allow us to do in the tumor world, and I get hints that this is already being done elsewhere but not openly published, is to, for example, doing serial imaging and combining what they call sort of 5D printing. So the 3 spatial dimensions and then additional dimensions where information such as growth rates or cell types or response patterns are also mapped onto the model as colors or textures. The modeling of mechanical properties is improving as we have better computational models and we're able to do more dynamic modeling. And the process is becoming much faster. So we're now able to turn around a model in about 24 hours to create the digital model, and the printing can take variable lengths of time depending on the technology used. This print took about 50 hours to put together. And there are some machines that can do it quickly at sort of 35 hours, but right now that's about the limit if you want that kind of size and that kind of resolution. And the next step is procedural guidance. So being able to actually not only fuse multimodal imaging, but actually project them onto the surgical field or have them available to the surgeon during the course of the operation. The big challenge with that has been to actually create viewing technologies that are not invasive, overly invasive or obstructive of the surgical work, and also being able to register the image continuously with the patient who's maybe moving, the organs may be getting shifted or retracted. And the infrastructure is obviously improving, so we're getting more and more evidence coming in. Guidelines are slowly being written. The PAC support is slowly being developed. So I want to sort of go through this fairly quickly and leave some more time for questions. I just want to thank Joshua Hansen, who's really quite essential to all this work, Max Maneri, who founded our lab, Dr. Patricia Murphy, who was quite essential in securing the funding for the lab, my department and the Division of Cardiac Surgery that have been very supportive, as well as the Division of Cardiology and the Petermann Cardiac Center Foundation. So, thank you very much.